Welcome back to the International Symposium on Accident Analysis and Prevention. So, we are going to start the second session, and the title of the second session is ICV Evaluation, Risk Perception, and Warning Strategies around, of course, the intelligent and connected automated vehicles. So, I am Professor Shimul Haq. Will be moderating this session. So our first speaker today is Dr. Jianghui Wen, who is an associate professor at Wuhan University of Technology, and her research interests are stochastic analysis and application, traffic big data analysis, and deep learning. Dr. Wen will be talking about a rear-end collision warning of connected automated vehicle based on a novel stochastic local multi-level vehicle optimal velocity model. So before I welcome Dr. Wen, please, given that we are starting a second session and probably we are having a different group of participants, I would like to remind you a couple of things. So for this special session, we have a poster session as well. And for that poster, the detailed instruction will be available through AIP website, and those posters will be displayed in the COTA conference in China in next year. And again, the way that we will be progressing towards this session is similar to the last session. So our speaker will be presenting first. After our speaker has been presenting, you can always post your questions with the Q&A button, not the chat button. I'm repeating it, put it to the Q&A button. Then I will be, at the end of the presentations, I will convey those questions to the presenter, and the presenter will answer. So without further ado, let's welcome Dr. Wen. So I'm now spotlighting Dr. Wen, and she will start presenting.
Okay, thank you very much, Professor Simon Hacker, for your generous introduction. Now I share my PowerPoint.
Would you please make it full screen, please? Yes.
Yeah.
All good.
Is it working for my PowerPoint?
It is good. Go ahead.
Okay, thank you. Good afternoon, everyone. I appreciate the opportunity to make this presentation here. Thank you for Professor Huang and Professor Li. The subject of my presentation is rear-end collision warning of connected automatic vehicles based on a novel stochastic local multi-vehicle optimal velocity model. My presentation is in 4 parts. It is known that traffic safety is directly related to human life. According to survey data, appropriately 60% to 70% of traffic accidents are caused by vehicle collisions, especially rear-end collisions. Most of them are serious incidents that cause a large number of casualties and considerable economic losses. Simultaneously, research indicates that 29% of traffic crashes occur when drivers fail to apply the emergency brake because they are unaware of the danger or have low reaction time. Therefore, improving the active safety performance of vehicles is one of the methods used to effectively prevent accidents. Connected automatic vehicles combine the Internet of Vehicles and intelligent vehicles, so they have some advantages. First, they are equipped with advanced sensors, controllers, actuators, and other devices that are integrated with modern communication and network technology. Second, through vehicle-to-vehicle, vehicle-to-infrastructure, and other communication methods, connected automatic vehicles are capable of complex environmental perception, intelligent decision-making, and collaborative control. Further, data that shows that collected automatic vehicles can correct the wrong behavior of drivers in the driving process, reduce traffic accidents by 90 to 95%. The economic loss from accidents was reduced by 48% in a collected automatic vehicles test from Huawei company. Therefore, studying a real and early warning method for connected automatic vehicles is a prerequisite for the development of vehicle loading, rear end collision warning systems. The use of such a method will be of great significance in reducing traffic accidents. Because we aim to research on the rear-end warning method for connected automatic vehicles, we overview the rear-end warning approaches first. Existing research has focused on the collision time method and the safe distance model. In the model, the reaction time of emergency brake is calibrated by simulating a driving test. Other influence factors, including driver reaction time and vehicle parameters, have been introduced to design a safety distance model. With the development of vehicle zone calibration technology, the safe distance model has been widely used in collision warning modeling and construction systems. Vehicle zone calibration technology can realize an information exchange between vehicles. A real-end collision and natural collision early warning model was proposed with time, position, speed, distance, and braking distance used as parameters. In summary, most previous workers have only considered the impact of vehicle parameters on real-end collision between vehicles, but they have not fully considered the impact of weather conditions, driver response, road conditions, and other external factors. These factors are incorporated into the influence of car following behavior. This to say, it is necessary to overview the existing car following models like IDI model, OV model. These above-mentioned models have different modeling values and application areas, which have promoted the development of research on car following behavior. However, connected automatic vehicles have their own characteristics. They can acquire all kinds of driving state information from multiple vehicles in a timely and accurate manner through advanced sensors and communication devices. They can also adjust their running states based on their devices to stabilize traffic flow and reduce traffic congestion. Thus, constructing a car following model in which the complexity of traffic systems can be described is worthy of research. Considering the interaction characteristics of connected automatic vehicles, the random factors of traffic systems, and the complexity of car following behavior, we intend to establish a stochastic local multi-vehicle optimal car following model of connected automatic vehicles with multi-vehicle information interactions. On this basis, a scenario is set involving emergency braking by a front connected automatic vehicles in the context of car following behavior. Then, the speed threshold of the rear-end collision warning is calculated. Now, I'd like to turn to introduce the methodology part. Our model is based on the BLVD model, which is proposed by Sun in 2012. The equation axis formation. However, the connected automatic vehicle perceives not only the surrounding information, but also the information outside the visual field through radar, camera, and vehicle communication equipment at the perception level. So we propose a local multi-vehicle optimal velocity model like this formation. Simultaneously, the entire traffic system is considered a dynamic and stochastic system with typical stochastic characteristic, and the sources of randomness mainly come from the road environment and the drivers. Stochastic processes are adopted to describe the influence of random factors. Therefore, standard one-dimensional linear processes are introduced in the LMOV model, named the stochastic local multi-vehicle optimal velocity model, like this formation. Since the stability analysis of traffic flow is an important index to evaluate the low degree of conformity models, the stability conditions of the LMOV model are induced like this. For the SLMOV model, we use Liablon function and obtain the sufficient conditions of CAV for the exponential stability of the second order SLMOV model. Since the SLMOV model is composed of deterministic and stochastic parts, a parallel estimation method is established. For the deterministic part, the nonlinear programming estimation method is introduced. The mean absolute error is chosen as the objective function to be optimized, which means it has the difference of the predict value of vehicle velocity and the corresponding true value of velocity. For the diffusion coefficients, we adopt the concept of regression analysis. The detailed step is step 1, a time series forecasting model is established, and the second step, a group of optimum weights is obtained by using the adaptive filtering method, and then the diffusion coefficient values are predicted. Okay. As shown in this figure, the emergency braking warning scenarios of two adjacent connected automatic vehicles were investigated. Known at the beginning time T0, the velocities of the following and the leading vehicles are V1 and V2 respectively. In the case of an emergency, the lead vehicle brings to stop with maximum braking deceleration A2. Safe distance refers to the appropriate distance between two vehicles in the same line and driving in the same direction. It can neither cause real-end accidents nor reduce road capacity. Based on the above-mentioned emergency braking process, and given the influence of random factors, the speed of the CAVs change in real time, and the corresponding safety distance also changes in real time to ensure that the distance between vehicles is greater than the minimum allowable distance dm during the whole braking process. The distance d between two vehicles at the initial time should satisfy this inequality. According to the dynamics formula, the driving distance of the following vehicle during the braking process is this equation. Then the D1 is a random variable. According to the definition, the distribution function can be calculated by probability theorem. From the definition of the self-distance, when D1 is smaller than D plus D2 minus Dm, the status is safe and can avoid the occurrence of a rear-end collision, then such that P0 stands for the probability of safe status. The equation of V1 and the critical status satisfy this equation. Its solution can be used to obtain the maximum critical value V max of the initial velocity of the following vehicle and the safety probability P0. Comprehensively considering the vehicle safety and the comfort of drivers, we give these methods to set a reasonable interval of velocity adjustment for selected automatic vehicles. Okay, I'd now like to move on to the results and the discussion part. The stability analysis results are divided into 3 parts. First, this figure illustrates that the stability curves of the models from high to low are arranged as follows: OV model, FVD model, BLVD model, LMOV model when M is 1, and LMOV model when M is 2. The compression results mean that the stability of traffic flow can be theoretically improved by considering the real value effector, multiple front-end vehicle information, and optimized velocity differences information of leading vehicles. The simulation results show that the fluctuation of vehicle velocity is small in the 6 groups of simulation experiments with different parameters. It can be seen that the fluctuation range decreases with time by comparing the distribution of vehicle velocity at different times in each group. Therefore, the LMOV model with appropriate parameters can gradually dissipate the influence of small disturbance to achieve the stabilization of traffic flow, which is consistent with the stability critical curve in the left finger. From this figure, results indicate that different road environments have a certain impact on vehicle speed in the following model. When the intensity of stochastic fluctuation is small, the system can maintain stability through self-regulation. However, when the intensity of stochastic fluctuation is extremely large, the stability of the system may be compromised, and the time-to-time stop phenomenon emerges. We use different sigma functions to study the influence of vehicle pedestrian carpooling and carpooling behavior on the running state of the motor fleet. It is found that velocity variance is mainly affected by the size of stochastic fluctuation. In addition, there's no obvious difference in the simulation results of the diffusion coefficient among the 3 different functions. Okay, the parameter estimation results are shown in this table. First, the prediction accuracy of the LMOV model is higher, then the parameters of the 6 vehicles are stable in narrow ranges, which can help direct the following model parameter setting according to the vehicle data. From the results of the action with P, we found that the drivers of vehicles 1091 and 1093 pay more attention to the lead vehicle during the driving process, whereas the drivers of other vehicles also focus on the operation status of the following vehicle when driving. However, in general, they still pay more attention to the status of the leading vehicles. The estimated results of gamma I show that the corresponding values of the 6 vehicles are small, which indicates that drivers usually pay more attention to the nearest following vehicle when they observe the real situation of traffic on those. From this figure, the width of the prediction interval is evidently small when the stochastic fluctuation is small. Otherwise, the width of the prediction interval is not, so the prediction curve, the prediction interval contains most of the measured data, and the width of the prediction interval is slightly large. This figure shows that the threshold curve of the following vehicle velocity is almost higher than that of the leading vehicle velocity, and the above vehicle adjustment time interval. The results indicate that under the corresponding conditions, the following vehicle's velocity can be appropriately higher than that of the leading vehicle, and the following vehicle can thus avoid a real-end collision with the leading vehicles. Simultaneously, the velocity differences between the leading vehicle and the following vehicle decrease when the brake deceleration levels drop. The figure shows the velocity threshold values. Different vehicles present various trains for the velocity threshold value. This table shows that the comfort degree of each vehicle with a variable velocity adjustment interval is lower than that with a fixed speed adjustment interval. That's to say, the comfort degree of drivers improves a certain extent. In addition, the velocity adjustment frequency of the two methods are compared. The variable velocity adjustment interval method improves the comfort of drivers without increasing the velocity adjustment frequency. And this figure shows that the comfort index curve increase with increasing adjustment time interval. The slope of the curve is small at the beginning and then suddenly increase between 0.4 and 0.5 seconds and then decreases. Therefore, a fixed adjustment interval can be set at approximately 0.4 seconds. Okay, that brings me to the end of my presentation. This work reaches the following 3 conclusions. First, a SLMOV following model is constructed considering a multiple information interaction of collected automatic vehicles and the influence of stochastic traffic system. Research indicates that these factors can be caused and presented as a stochastic fluctuation intensity. Second, an early warning method for preventing real-end collisions is proposed through the relationship between vehicle velocity and the probability of real-end collisions. Third, a method for setting the interval of speed adjustment in real time is established according to the characteristic of collected automatic vehicles. Well, that's about it for now. Thank you very much for your attention.
Thank you, Dr. Wen, for the nice presentation. So we have received a comment from Jianming Li, and Jianming commented that your presentation was very good, and the figure that you have presented are very beautiful. His question is, what programming language or software have you used for your analysis?
Okay, we do our work used the MATLAB software. MATLAB, yeah.
Okay, so that's good. And I have a follow-up question, but in the meantime, I have received other questions from Amjad Parvez. Amjad's question is that the current study is based on the simulation, right? And
Yeah.
the real world CAV data is not used in this test. So do you expect that results will be applicable to the real world CAV data?
Actually, we use the NGSIM data to do our work. Because this work was done last year, so we use the NGSIM data. And now we did some cooperation with the Professor Jianghui, who did the presentation in the morning. They built a simulation platform of connected automatic vehicles. But now in our university, we try to do some real-world experiments to obtain the data.
Okay,
it's our future work. Yeah.
Okay, thank you so much, Dr. Wen. So I think we should move to the next presenter now. Could you please stop sharing your screen and off the video, please, Dr. Wen?
Okay, thank you.
Thank you.